Good morning, it's Dan Tanning from ICLR. This morning we have Ryan Ness, who is the Senior Manager of Research and Development at the Toronto Region Conservation Authority. He's going to be talking about climate data in Ontario, but for those of you who are not located in Ontario, the information he's going to talk about certainly will be relevant for others interested in climate change data and climate modeling and that sort of thing. This is the last Friday forum of the year, and we don't quite have the schedule together for next year, so watch your inbox, and we'll have that out pretty soon. With that, I'll pass it over to Ryan.
Thanks, Dan. And where am I looking at a webcam?
Webcam, right to integrate with.
Okay, perfect. Thank you. So, as Dan mentioned, I'm with the Toronto Region Conservation Authority, but I'm also here representing the Ontario Climate Consortium to talk about the current state of affairs, as it were, around climate data and information in Ontario and its use. Some of the good and challenging things associated with the state of practice, and as Dan also mentioned, I think what's happening in Ontario is a bit of a window on what's happening generally in this field. So hopefully it will be broadly applicable to anybody on the phone who's not from the province. Quickly, a bit of background on the Ontario Climate Consortium. It's a collaborative of researchers and end users across the public and private sector and nonprofit sectors in Ontario that was founded by York University and the Toronto Region Conservation Authority to try to enhance the state of climate change impact assessment and adaptation practice in Ontario, to try to connect researchers, scientists with the end users of data in recognition, and in terms of much of what I'm going to talk about today, of the fact that connection wasn't happening, perhaps to the detriment of the quality of work being done in practice. The three program streams of the Ontario Climate Consortium, which is coordinated by the Toronto Region Conservation Authority, are climate information, the derivation and provision of climate information to end users, support with impact and adaptation studies, and a broader effort, particularly on behalf of our academic partners, to mobilize research and information in the end user community. Our key partners are on the left: the York University, the Region of Peel, University of Guelph, and McMaster University, as well as the Toronto Region Conservation Authority, who is the secretariat and coordinator for the consortium. And these are two examples of projects that the consortium has undertaken, of dozens that it has over its nearly 10-year life now. The State of Climate Change Science in Great Lakes Basin project is an example of climate information and state of practice work that the Ontario Climate Consortium does, often on behalf of other levels of government. The climate change vulnerabilities assessments of community service and assets in the Region of Peel is an example of applied climate risk and vulnerability assessment, the use and application of climate data in adaptation planning. For my presentation today, I'll talk about climate information, what that means, and why we need it, and why it's become particularly important in the recent history of practice in the insurance industry, and engineering and planning and design. The state of climate data and information in Ontario, where it comes from, how it's used, who's using it. Again, I think those findings are transferable to other parts of certainly Canada, if not globally. And some thoughts on some of the challenges that exist, some of the pitfalls associated with the current state of use of climate information and data, and how we might move forward. So, kicking off, what is climate information? Why do we need it? For those who are on the line, who are in the insurance industry, certainly not a mystery as to why climate information is required. We, as a society, plan, design, respond, dedicate resources, assign priorities based on what we expect climate conditions to be. Examples showed up here. Heat units for agricultural planning, wind loads for building design and building codes, and rainfall frequency to plan for flooding and flood risk and other risks associated with extreme rainfall. Certainly, the insurance industry is no stranger to climate information in the use of and development of insurance products. But of course, the world is changing. That the climate information that we used to use based on historic information and assuming that historic conditions would continue into the future is no longer a valid assumption. We know that the climate will change around the world, not only temperature, but bringing with it changes in other forms and types of climate and meteorological conditions, wind, rain, cloud, sun, drought, and all manner of potential changes to the patterns of weather and climate that we've known over the past several centuries. And climate change adaptation is very much in the fore right now. The process of planning for that different climate future, assessing means to all manner of societal activities, and reflecting that in planning processes, design of infrastructure, programs, services across the public and private sector. And climate change science and climate change data and information is a critical element of that process. Climate information is more than just data, although it includes data. This is a definition we find very useful from the United Nations Environment Program that describes the elements of climate information. So it is the data, whether it's observed or modeled, synthetically created data, but also analyses of that data, trends, statistical indices of that information that help us understand what it means in particular applications or its impacts to particular systems or human communities. And lastly, and very important, the information that's required to interpret and use these data sets, which is often left off the list and part of the challenge in terms of how climate information is applied, which I'll talk about more. Sources of climate information for climate change adaptation planning and assessing impacts is part of that. There's the historical information to be able to understand what we experienced in the past and how our systems responded to that, and then future climate projections to try to understand what the future may have in store. Historical data is again, to the folks in the insurance industry, I'm sure very well known in terms of the types of information that's available. There are meteorological stations around the world that collect information in great detail. There are great records in Canada as in other places, although the number of stations and the quality of even has declined with less investment over the past couple of decades. But extensive information is available, and that's in the form of individual station records. There are trend analyses on that data, which can point to some of the trends that we may expect to continue in the future with climate change, and there are convenient products that roll up data at a geographic scale, like this example of gridded, interpolated historic climate and temperature data for the region of Peel. And then on the projection side, projecting future climate, the primary means of understanding what the climate might look like in the future has been climate models, and I'm sure most of us have heard of the climate modeling efforts that have been made. Most of the projections and numbers in the media about the amount of global warming and the types of temperature and precipitation and other types of weather changes that we'll hear come from these global climate models that are developed and run by 20 sort of first-tier recognized modeling centers around the world. So there are 20 legitimate, recognized global climate models, or at least 20, the number's kind of in flux, that are run at a very large scale, and modeling is also increasingly done at a smaller scale within those larger models called regional climate models, which I'll talk about a little bit more as well. So not only are there 20 different climate modeling centers that may run one or more climate models or types of models, all of which run a little bit differently and generate different results, but then there's, as we know, a lot of unknowns around what society is going to do around greenhouse gas emissions, and those climate models try to incorporate that uncertainty by running a number of different scenarios of future emissions and concentrations of greenhouse gases in the atmosphere, which vary quite significantly. So you can already start to see about the number of combinations and permutations that might exist in terms of trying to model future climate. There's a lot of discussion around downscaling nowadays. Downscaling refers to processes of trying to take that large-scale global climate modeling and translate it into information that's more relevant on a site-specific or smaller area basis. And that's done in a couple of different ways, sometimes combined. The first is the use of regional climate models for dynamical downscaling that can reflect many more local, topographic, and water resources, for example, the Great Lakes system's effects at a more local scale, and can give information that may be a bit more valid locally. Statistical downscaling is also often used. It's quite a lot less computationally intensive, and it tries to establish statistical relationships between large-scale and local climate variables and apply those relationships to the downscaling of future projections of those large-scale climate variables in climate models, global climate models. And it's not a simple task to understand what kind of information is required, and depending on the type of climate change adaptation planning that is taking place, different types of information are required. Basic adaptation planning, looking at general trends to assess high-level risks and changes, require basic information, but if one wants to look at advanced impact modeling and quantitative analysis, a very different type and level of information is required. And as you try to get into that increased level of precision and specificity in climate information, you also increase the complexity of the parameters you're looking at, the level of effort that it takes to derive that information, and the uncertainty associated with that information. All of those go up as you look into more advanced assessments of what climate change might mean and how to respond to it. This is a really excellent piece from a guideline put out by our colleagues at Uranos, a consortium in Quebec that focuses on climate change information and adaptation practice. They put out a manual of helping practitioners understand what climate information they need for specific purposes. And it depends on a number of questions, not only what is needed for the particular type of assessment that's being undertaken, but what is the user able to process, and that's often a bit of a disconnect. The technical capabilities of the users are often not aligned with the types type of data that they actually need. And this is a flow diagram from that document. The words themselves aren't important, but what this is intended to convey is that depending on the type of application, there are some fairly complex decisions that need to be made around figuring out what climate data to obtain and how to use it. I'll talk now about how climate information and the types of climate information that we're talking about are being used in Ontario as hopefully a bit of a case study of the state of practice, not only in the province, but more broadly. We certainly feel confident to say that it's similar to the state of practice in other provinces in Canada and likely in parts of North America and Europe as well. In Ontario, users have access to a number of different sources of climate information, which on the historic side of things is both good and bad. Environment Canada has extensive data archives as the sort of primary public body that collects and maintains climate databases, but there are also other public and private monitoring networks, particularly over the last couple of decades as private data collection has become more economically viable, and organizations like the Weather Network have come online with their own networks. There are also a number of different data products out there that have been generated to provide that information to users in a convenient gridded form, like the one I showed earlier for the region of Peel, which is great for users. But there are at least 14 of those products out there, all of which have slightly different resolutions and drawing slightly different types of data and use different techniques for interpolation and gridding, which creates a conundrum for users in deciding what to use. On the future climate projection side of things, there are at least, to our knowledge, 21 different publicly available future climate data sets that reflect various numbers and combinations of global climate models and regional climate models. Some of them have been statistically downscaled. Again, great that there's this much data, but there isn't one definitive product or service out there that says this is where you go to get climate change projections for Ontario. And in addition to those that are produced by various government agencies, research institutions, both on the Canadian and American side of the border, because most American work at least covers good chunks of southern Ontario as well. There are custom analyses by agencies in the provincial government, in the federal government. Individual universities are doing their own analyses and downscaling for particular studies, and increasingly the private consulting industry is doing that as well. We, as I mentioned earlier, did an analysis on the state of climate change science in the Great Lakes Basin, and we take this as, while the state of practice we assess extended beyond Ontario into the United States side of the Great Lakes Basin, we feel that the results are pretty indicative of the state of practice, specifically in Ontario. So these are the different types of work that climate information is being used for in the Great Lakes Basin, and you could assign the sort of same proportions to work in Ontario, primarily on water levels in the Great Lakes, but also surface hydrology, flooding, flood risk. Those are the majority of studies being conducted out there, or the largest number of studies being conducted have to do with those types of systems and impacts, ecological systems, independent sort of climate and analysis and modeling studies to generate more specific data, and the list goes down. But interesting to note that the primary application has been in water and water-related issues. in terms of the climate projections that Ontario users are applying in their work, Ontario and Great Lakes Basin users are applying in their work, it varies. On the climate change emission scenario side, as I mentioned, that these climate models run with various scenarios of future greenhouse gas emissions and concentration of the atmosphere. Many users are still using an older set of climate emission scenarios. The A1, F1, A2, those that have alphanumeric characteristics like that are the older data sets. There's the new representative concentration pathways, which are the sort of new international set of modeling results that are being used in current discussions, are slow to be used in applications in Ontario and the Great Lakes Basin.
So can I ask a quick question?
Sure.
The A2, how does that compare to the RCPs? Like, is it 8.5 or? Around 8.5.
Yeah, it's not, and they don't line up exactly, which is difficult, but there are, as there were in the sort of the fourth assessment report model, emission scenarios, the A1, A2, B2, etc. There are sort of optimistic to pessimistic gradations along that spectrum, but I think the entire spectrum of scenarios has shifted to be more pessimistic than it was previously to some degree. And the important thing, I guess, is that they don't line up exactly with each other, which creates sort of a different or an additional source of uncertainty or disconnection in different modeling studies.
With respect to those scenarios, sort of 157, these are 157 studies, or what is that?
Yes.
Okay. And are there certain types of studies that tend to prefer using the more severe scenarios like E2 compared to some, you've got 23% using B1, 18% A1B, do hydrology studies tend to use the severe scenarios?
It's a good question. I'm not sure if we've done that level of analysis, but something that we have the data for and we could easily draw out. Looking at the actual global climate models that practitioners are using in their climate change impact and adaptation studies, again, there's a lot of variability. The acronyms aren't important. Those just represent different modeling centers in different countries around the world, as I discussed earlier. And certain models are clearly more popular than others. The Canadian global climate model is often used for studies in Canada, perhaps not surprisingly, but what's often forgotten is that there's no evidence to suggest that the Canadian global climate model is necessarily any better at predicting Canada's climate future than any of these other models. They all model the entire globe and don't necessarily focus on the area in which the modeling center itself is located. The use of large groups of models to look at a variety of outcomes is fairly rare, even though that's the practice that's recommended by the Intergovernmental Panel on Climate Change and others. It's more common for practitioners to use small ensembles or even single models. And from a downscaling perspective, the practice is also quite varied. A number of, only 14% of the studies that we analyzed are using dynamical or regional climate modeling with downscaling. There's a lot of statistical downscaling being used, different techniques. Statistical downscaling has its own assumptions and uncertainties associated with it. The observation, weather generator, and delta method there as well are other forms of more simple statistical downscaling. Statistical downscaling is certainly dominant in terms of practice. Just generally from that study and from our experience with the Ontario Climate Consortium and at TRCA and working on climate change adaptation, in Southern Ontario and across the province, our sense of how Ontario users are deciding what climate information to use and how they get it, it's somewhat ad hoc. Word of mouth is certainly a dominant means of those decisions being made. Studies that have been done by partner organizations, informal networks, and communities of practice that have sprung up, but in the operative word being informal. Convenience and familiarity of sources. For example, the Canadian Global Climate Model is more accessible to most Canadian practitioners than some others. And there is some guidance and information from expert organizations like the Ontario Climate Consortium, URANOS, the Quebec Climate Consortium is quite active in Ontario as well. But that's not always, those resources aren't always being drawn on. So there are some obvious challenges and pitfalls emerging that I'll summarize, as well as some thoughts on how to deal with those moving forward so that we can ensure that the standard of practice is in Ontario and elsewhere is consistent, and that we can compare outcomes of different types of studies on an equal footing. So one of the big challenges that is emerging is that practitioners aren't dealing with uncertainty. Climate modeling, as I think I've illustrated so far, is fraught with uncertainty. The number of different models, the number of different emission scenarios that are considered, even one model itself, when run 5 different times, will give you 5 different outcomes because of the complexity and the degree of sort of random processes within the model. This graphic on the left shows how that uncertainty plays out just in terms of trying to project future temperature changes at the global scale. So you've got the individual model uncertainty in the middle here, which in and of itself, that's the uncertainty associated with running the same model over and over, in and of itself is about 0.25 degrees of uncertainty in terms of projecting future climate, which on the global scale is quite significant. Then you've got the spread between different models, even if they're running the same emission scenario, and then when you include the different emission scenarios in the mix, this is the entire envelope of future projections at a global climate scale that we're working with, from virtually no temperature change to a potentially sort of extinction level of 4.5 to 5 degrees or more. And I should mention that these are I think, representative of the AR4 report. So the current projections are much more pessimistic, and you'll hear a lot about 6 degrees warming, which is where some of the climate models are now going, which is a catastrophic, certainly an extinction level type of change for the world. The graphic on the right shows on the y-axis the strength of the signal of climate models versus their uncertainty in terms of what they tell us in different parts of the world moving forward. The different parts of the world aren't that important. You can focus on the black line at the top. Basically what that says is that the magnitude of change suggested by the models, say in, let's look at 2100 time period. So if the climate models are suggesting on average a temperature increase, say, of 3 degrees globally, the signal to uncertainty ratio is almost 1, which means that there's a plus minus on that of 3 degrees. So we expect 3 degrees of global, if we look at global climate models, we expect 3 degrees of global temperature warming plus or minus 3 degrees, which
that is AR5.
That is, so the right graphic is AR5, so that's even the most recent set of climate models that are now currently under discussion.
Sorry, and then what would that mean at 2? Like at 2020?
At 2020, so at 2020 it means if they're predicting 2 degrees global temperature warming plus or minus 1 degree. It's the ratio of that projected magnitude versus the uncertainty associated with that. So obviously uncertainty increases as we move out into the future. The climate emissions scenarios and climate models themselves get much more uncertain as you run them over long time periods. This is another illustration of uncertainty dealing with precipitation, which is one of the issues we deal the most with at the Ontario Climate Consortium and Toronto Region Conservation Authority, showing how uncertainty cascades, just looking at global climate models. This is from a study in Asia over a large river basin, trying to assess the different annual precipitation changes that might occur in the future over that basin. So as you move, looking at different emission scenarios, and then you run those through different models, the uncertainty expands. Then you run then there are different runs of those models themselves, and as I mentioned, you run a model 5 times, you get 5 different outputs. So this is sort of how the spread of outcomes increases and the uncertainty increases. So what you see, and this is just even before any kind of downscaling effort, this is just looking at global climate models, what you see in, say, the 60 to 100-year period from now, the uncertainty is anywhere from minus 25% decrease in precipitation to a plus 40% increase in precipitation. Obviously, it's a massive range, and if you pick sort of a single or even a small subset of those scenarios, you'd be clearly missing some of the important possible future outcomes. Another challenge that we see in Ontario, but I think this is pretty universal, is the challenge of scale mismatch, especially in that global climate models, which are still relied on heavily for a lot of studies, don't generate information at the scale that is needed to look at particularly local impacts. If you think about the case of different types of climate patterns, and those that are often talked about in terms of climate change and climate change adaptation, think about the very damaging thunderstorm-based flood events that have happened in Toronto over the last decade or so, with hundreds of millions of dollars in insurance payouts. The scale of those systems is the 10-kilometer or 10 square kilometer scale, maybe 100 square kilometer. When you look at global climate models, the size of the grid cells that are computed in the model is on the order of 10,000 square kilometers. We're essentially in any given climate model given the same climate output as Kingston or Pittsburgh, but we know we have very different climates in both of those places. So the inability of climate models without significant downscaling effort to depict the types of processes that we're really concerned about when it comes to adaptation and different types of meteorological and climate extremes is a big challenge and is not being directly addressed or at least consistently addressed in Ontario and elsewhere. To illustrate this a bit more, some of these challenges through a case study that the Ontario Climate Consortium took on, McMaster University and Waterloo University leading, partnering with Essex Region Conservation Authority, the Toronto Region Conservation Authority, and the local municipalities within those two regions. Looking at intensity, duration, frequency curves, a product probably well known to most folks who deal with water-related and storm-related risk in the insurance and sector and others. Statistics that analyze historic extreme rainfall patterns and tell us, based on those statistics, what we might expect if that historic climate was going to continue in the future. Might be the intensity, say, of a 2-hour storm with a return period of 100 years. So commonly used in design. Storm sewers, for example, will often be designed to convey the maximum, say, 1-hour storm, the 5-year 1-hour storm as an example. Before I move on, just should say that there is a lot, because intensity, duration, frequency statistics and curves are relied on to a huge degree in engineering design, drainage design, flood management, and aspects of flood risk management. There's been a big push to update these curves to incorporate climate change as a means of adaptation. There's a hope that these can simply be revised upwards to reflect a future climate, so that infrastructure and systems and warning processes are adjusted accordingly. But it's a bit trickier than that, as I will show. The objectives of our study were to look into the implications of using different methods for incorporating climate change into IDF curves, because it is something that's being attempted across Ontario, across Canada, and around the world, but often using very different methods and techniques. And as I hope you're beginning to understand, based on our discussion of climate data, there's all kinds of different future climate scenarios that you could plug in to this kind of exercise. So we wanted to develop an approach to compare the outcomes of applying different permutations of climate model outputs and different methods of deriving IDF curves, some of the different methods that are out there being used in practice in Ontario and elsewhere. And to use this approach to look at different outcomes of using these alternative permutations in both the Essex and Toronto regions. This is our study area. A number of stations in and around Windsor, and the Essex area and the Toronto area, and somewhat further afield, although we didn't end up using stations any further west than Oshawa, east than Oshawa. And this is a very simple summary of the process that we followed. We looked at the application of 5 different climate models that are widely used in practice in Ontario in climate impact studies, 2 global climate models and 3 regional climate models. We looked at 1 to 2 emission scenarios, greenhouse gas emission scenarios for each one of those models, and then we picked the 2 methods that are being used most often for downscaling and calculation of future rainfall IDF statistics. So those are the 2 methods that we felt were being used most widely in that practice, for a total of 16 different mutations. And the results, probably not surprisingly, are that there's a huge spread in the outcomes of calculations, using different combinations of emission scenarios, of models, and of methods for calculating future frequency of different types of extreme rainfall. So this just shows 4 of the potential 16 scenarios that we examined. Just for illustration, it gets crowded if you plot them all. The historic intensity, this is for 2-hour storms, is plotted in this bottom curve here with the blue diamonds, different return periods along the x-axis. So you can see the historic, say, 100-year 2-hour storm was in the order of 40 millimeters. Depending on which of the techniques and permutations is used to calculate the future 100-year 2-hour storm, you're looking at between 48, say, and 90 millimeters, which is obviously a massive difference and would have a massive impact on planning and design in terms of trying to provide, say, a storm sewer pipe that can accommodate the 45 millimeter storm versus a 90 millimeter storm. And as I mentioned, these are only 4 of the 16 permutations we looked at. The 16 permutations that we looked at are probably a very small subset of hundreds of different ways that you could look at future intensity, duration, frequency curves.
Was that example of the 4, is that sort of the spread of from the low to high? Yeah,
I think I'm pretty sure this shows pretty much the maximum spread from those 16 permutations. But the spread is certainly high enough. So we're trying to figure out ways to communicate those outputs in the format that engineers and practitioners are used to in terms of showing the spread between the 10th and the 90th percentile. in the gray band here of the future projections, and as you can see, sort of in the 2-hour storm, this is a different location than what I just showed, but in the 2-hour storm, in the 100-year return period, and in this example, there's a plus or minus 50% spread in the output. So that's certainly an interesting finding, and I think what it is suggests to us, as I think many practitioners in the field knew for some time, is that there's a huge amount of uncertainty in trying to assess, especially future extreme climate conditions. That's not resolvable. There's been a huge amount of effort expended on trying to refine projections of future climate, downscaling, regional modeling. They're all important technical and scientific exercises that can tell us more about the range of outcomes that we might expect, but that uncertainty is always going to exist. It's not that improvements in science are going to be able to tell us with more precision what the future climate is going to allow us. And to focus on that, we think is a bit of a red herring, in part because that uncertainty is irreducible. It will never be completely addressed, as well as the fact that there are other sources of uncertainty in the climate adaptation process. So the red box just encompasses the uncertainty associated with trying to get climate projections at the scale of a local or regional impact study. But then there's a whole other set of uncertainties associated with the modeling and assessment of impacts. If you take hydrological modeling, for example, the modeling of flooding and flood flows, that has a huge amount of uncertainty associated with it, as well as does whether or not impacts will actually play out in certain ways to communities and economy, as well as whether or not the adaptation responses we develop are going to be effective. Uncertainty is everywhere. It's not going everywhere, and if we only focus on trying to reduce the climate model's uncertainty, we're sort of ignoring that fact. So what should we do? Well, these are a couple of examples of work that we think sort of cuts through that and starts to deal with what we can deal with. First is projects that look at focusing on the greatest risks. The City of Toronto and their basement flooding program isn't agonizing over whether or not the future 100-year storm is going to be 60 millimeters or 90 millimeters. They're going into the areas of the city that are that they know don't have any kind of redundant or safe overflow out of the storm sewers into rivers and streams and ravines, which is what happens with new development. And so they're taking those older areas and they're just trying to push in as much capacity to convey flows safely as possible, because they know the risks of when the existing drainage infrastructure fails are extremely high in those areas as compared to others. So managing based on risk and outcomes and maybe deciding what number that you pick out of the range of potential future climate scenarios, you may base it on risk. And when the implications are $100 million worth of basement flooding payouts in a particular area as a result of the storm sewer system being overwhelmed, maybe that's a place where you take something at the higher end of the spectrum. Another example of the types of solutions that we think are important and are being talked about in climate change adaptation response are solutions that are flexible, that are functional in a variety of future climate scenarios, and even if the extreme sort of pessimistic scenarios don't transpire, they still provide other types of benefits that are really important in terms of a sort of a no-lose situation. For example, in low-impact development, stormwater management, the features and infrastructure that are created have all kinds of other aesthetic, biodiversity, and environmental quality and health benefits, even if, say, this bioswale at the bottom, it never reaches its design capacity. If it were to be designed for an extreme climate scenario, it still adds a lot of value and function, regardless of whether or not its capacity is ever maximized. So, some concluding thoughts based on what we've talked about in terms of how we deal with this uncertainty and how we move forward. Backing up a bit to the discussion of the status of climate information in Ontario, but again, relevant to other parts of Canada and the world where people are trying to plan for a future climate. The availability of climate data and information is generally not a problem. As we mentioned, there are dozens of sources of both historic and climate information publicly available for free to anyone. But the challenge is really to figure out how that data gets applied and which data to pick. What data is required for specific applications, what data sets should it be extracted from, and how can it be used appropriately. That's not guidance that's widely available in Ontario. Other provinces are certainly doing better in that where they have government-funded centres of excellence to try to provide those kinds of services. Quebec and BC are examples, but still, those centres can't help all users, and not all users are accessing them.
Sorry, what are the centres in Quebec and BC?
So there's a centre called Uranos in Quebec, and there is one called PCIC in the Pacific Climate Impacts Consortium in BC. So they are both of which have received very generous government and private sector endowments to do their work, and they have huge numbers of staff and computing resources as well. But that doesn't currently exist in Ontario and in most of the other provinces across the country, and in many parts of the United States as well. Another key piece of the puzzle in terms of help with application is around what shouldn't be attempted with the data. There's a lot of work. Climate data is out there. Anybody can access it. Anybody can do analyses and run numbers that give output. But whether or not those analyses are valid, are useful, is something that is difficult to ascertain. There is really no authoritative source of guidance out there on that, other than sort of a community of experts that isn't necessarily all that accessible to users. So there's an ad hoc environment of the use for the use of climate information in Ontario, and again, I think this extends to other jurisdictions in climate change impact assessment and adaptation planning, and this is likely leading to, certainly leading to inconsistent methods being applied in different impact and adaptation studies, and as a result, their findings can't be compared on an apples-to-apples basis, which makes it difficult to set priorities at a regional, provincial, or national scale, certainly. There is insufficient reflection on uncertainty and accounting for uncertainty in those assessments and planning efforts, and a lack of recognition of the importance of scale and the potential for scale disconnects between the climate information that is being used and the study that's being undertaken. This could be, and this is certainly a hypothesis more than something that is proven, and it's difficult to prove, but this could be leading to inefficient or ineffective investments in adaptation measures. It may be leading to overinvestment in some cases, underinvestment in others, and a misidentification of priorities. And lastly, and we know this well, it's in many cases it leads to inaction. When you present a practitioner with an output of a study that shows that their future 100-year storm can vary by 100%, it's pretty daunting to think about how to move forward in managing that. And in many cases, action is put off either in hope of better science in the future that will narrow that uncertainty, but as I talked about, that it's not likely to happen in any significant way, or just as the pushing off of a particular priority in favor of others that have less uncertainty associated with them. So looking ahead, as we've discussed, climate change projections are highly uncertain and are going to stay that way. Science is really evolving on climate modeling. There's all kinds of things that can be done with it, but it's not significantly narrowing the range of outcomes that we can plan for. An exclusive focus on climate data and information, on modeling, on projections, can be therefore counterproductive and can lead to inaction because there's nothing to wait for when it comes to uncertainty. And good adaptation planning, as a result, and this is nothing new to the practice of adaptive management and adaptive planning. These were principles that existed far before we knew we had to plan as a society for a different climate in the future. But good adaptation planning should lead to flexible and resilient solutions, not just, for example, over-designed engineered infrastructure. And I bring us back to the example of low-impact development, stormwater design, that those low-impact development features add capacity and function to the traditional engineered drainage system that provide other benefits without having to just dramatically upsize and over-design the hard engineered infrastructure itself. So this brings me back to the mission and objectives of the Ontario Climate Consortium and others in Ontario who are trying to elevate the practice of adaptation planning and climate change impact assessment. We're trying to equip decision makers across the public and private sector with data and climate intelligence, sort of expert advice on how to interpret and apply that data so that we can make efficient and effective responses to climate change in Ontario. We're trying to provide an access for users to climate change expertise in Ontario through connections to universities, as well as provincial government departments, which I didn't mention before, also participate in the Ontario Climate Consortium to try to generate high-quality climate data and intelligence that stakeholders can use not only on adaptation, but increasingly on mitigation, climate change mitigation projects, and to try to build a world-class climate industry in Ontario, because we do have a lot of capacity. We have very, very well-known academic institutions that are at the forefront of both climate science and climate adaptation practice. But the connections need to be made to provide access to that expertise to the end users and the stakeholders that need to act on it. Thank you.
Questions? I've got questions. So in your opinion, there's lots of uncertainty in it, and like you said, this is leading to inaction. And there was I guess a group in MOE that was looking at this a few years ago, a stakeholder group, and they said, despite the uncertainty models, we need to do something about climate change right now. But the big barrier is managing this uncertainty, and we need like a guidance, like the centralized guidance for municipalities, so that you talk to any engineer in a municipality, they know it has to be something, but there's nothing to sort of anchor on to help with this uncertainty. So who do you think should develop this information, and what form might it take, and how could we do it?
Well, ideally, I think it would be the senior levels of government that would step up and provide this guidance, as they do for other aspects of the use of at least historic climate information, the building code, stormwater management design standards, etc. It's always easiest to legitimize a particular guidance piece and have it applied widely if it comes from that top down. Not that they would be the only, they would bear the burden entirely of its development, but in terms of its endorsement and legitimization, Environment Canada at the senior level, at the federal level of government, the MOECC, MNRF, who does a lot of work around flooding and flood risk management. Those are the bodies that we hope step up to provide the consistent guidance that is required.
So something like the 2003 drainage manual, and doesn't have to be regulation, just guidance trying that.
Absolutely, yeah, it certainly doesn't have to be regulated, but it helps to ensure consistency when, again, the province or the federal government come out with a guidance piece.
Yeah. Other questions? Another thing was, so there are a couple of municipalities in Ontario that I'm sure you're aware that have sort of made changes to their design standards, IDF curves, to try to account for climate change with Barrie and kind of come into mind. And they ended up sort of just selecting an increase in intensity in plumbing for possible, which would be not necessarily the best way to go, but they don't have a lot of other options at this point. Have you seen really good work from other municipalities, progressive, consideration? You mentioned Toronto, who doesn't actually have an official climate change, impact sort of incorporated into their planning and so on, but they're just focusing on risk. Would you consider that to be the best approach at this point, or you say?
I think so, or at least it's a critical element, sort of risk-based planning and design. As I mentioned, sort of the spread of future outcomes perhaps is something that science and research can help refine, but it's always going to be a spread. But perhaps if that's well known and fully explored, then at least municipalities and others may know the upper and lower bounds of the potential future and apply something in that range based on the risk of the particular application.
Right. So, privacy also comes to mind because they focus on specific infrastructure components. And if you're to take that spread, keep it in mind while you're planning a hospital or something like that, you might think about the more severe scenarios. And if you're building a soccer field beside the lake, you can think about the less severe scenarios.
Absolutely. And that's, there are disciplines and professions that have traditionally used risk-based planning. It just seems to that philosophy seems to have not entered the discussion yet, particularly around drainage management, but certainly in other aspects of climate change adaptation as well.
For Vancouver, since they just came out with their strategy to go 100% renewable, and I think they're going to have a more detailed plan coming out in December. I mean, if they're that far along on going 100% renewable, they must be also far along on adaptation, and particularly they're on the coast. So do we know whether there's learnings from Vancouver? They seem to be the most progressive.
Yeah, they're worried about different things than we're worried about in Ontario as well. Sea level rise is their number one climate change adaptation issue, which we fortunately don't have to be dealing with. I think in terms of just adaptive planning, I think they are showing some leadership there. Its applications are mostly to the sort of coastal flood risk, but in terms of planning communities based on risk, incorporating climate change, they've got some interesting stuff that they've done there from a sort of philosophical perspective and in terms of what could be applied to different places.
I mean, just looking at the range of potential outcomes, like mitigation. I mean, I know we have to balance both mitigation and adaptation, but, if Toronto can get to a point where we commit to go 100% renewable by a given date, that'd be good.
That's an important point not to forget is that
there's no way we can adapt to 4 or 6 degrees of warming. So
yeah, it will be catastrophic. There will there will be bad things will happen if things get to that point. So we can't forget that there is a range of outcomes beyond which we just can't adapt to as a society. We might be able to build drainage infrastructure for it, but that doesn't mean that we're going to like the place that we're living in that has those new storm sewers.
And on the the topic of dealing with uncertainty, and I apologize, I was late, Karen Lockridge from Mercer. And so I've been involved from an investment perspective. How are investors looking at climate change and the range of uncertainties, and what do they do, in developing a climate change strategy for their portfolio? And really, when you look at emissions pathways, I mean, you just really have to develop scenarios and just do a scenario approach, and then, okay, if this, take a deterministic emissions pathway, and then model, I mean, you might look at uncertainty, okay, how might the, and you can even build this into the scenario, how might the physical environment adapt or respond to that emissions pathway, and then take that as a given. Okay, how might the portfolio respond to that?
Yeah, absolutely. And one way that seems to be emerging to do that is to first develop the scenarios not based on climate projections, but to assess in terms of a business or a service or a community, what are the thresholds of significant disruption, loss of life, etc. And then going back to the climate scenarios and saying, okay, how many climate scenarios push us over that threshold as well? Is it all of them? Is it 1% of them? That sheds some light on sort of whether or not a particular negative outcome that crosses some threshold of performance or adaptability will occur.
So, Ryan, with the TRCA, I mean, this group here primarily, well, at least from my perspective anyway, primarily relies on the flood zone information that you guys provide for the region here in Toronto. And to what point are you currently using these climate change projections to impact your flood predictions in your official maps?
We're in a way, we're lucky in Ontario and particularly in the Toronto region because our flood maps are plotted based on an extremely rare type of storm and flood event. As I'm sure you know, Hurricane Hazel is sort of the basis for most of our floodplain mapping in this part of Ontario. That's it's so rare that or so much of an outlier that it sort of defies statistical analysis, but people estimate that to be somewhere between a 750-year to 2,000-year sort of storm.
Well, it's interesting that you kick out those numbers because, I mean, that's where I'm inclining to be right now, to agree with those numbers, but a handful of years ago, we wouldn't have heard those numbers. We would have heard 350 years. So, is it change in those?
On Hurricane Hazel? There are parts of the...
That's my recollection.
There are parts of the province, and there are types of applications where the 350-year storm is a standard, but that would be separate from Hurricane Hazel. But it is an excellent question in that, sort of, one, what can climate change tell us about storms like Hurricane Hazel occurring in the future and their probability? And on that front, climate science is not very advanced in terms of predicting the probability of a hurricane tracking up the west side of the Appalachian Mountains and colliding with an Alberta clipper or whatever the situation was that occurred there. So that is a gap, but we feel at least where Hurricane Hazel defines our flood risk zone that we've got some conservatism there because of how improbable it is. But there are parts of the province and even parts of the urban areas in the Toronto region where it is the 100-year storm that defines the floodplain. Or there are locations where storms like the ones that we've experienced over the past last 10 years, even though they're much smaller in spatial extent than Hurricane Hazel was, which sort of blanketed the entire region. Locally, they can generate flood flows that are higher. Cooksville Creek in Mississauga, as an example, for those who may have heard of that. That's the adjacent Conservation Authority's jurisdiction, but by their calculations, I believe it was the July 8th, 2013 storm exceeded sort of the Hurricane Hazel flood level. So there is the need to look at, especially in those areas where we've got a 100-year standard or where recent storms are creating flows higher than Hurricane Hazel in those localized urban contexts, how we define the flood risk zone. That's very much on conservation authorities' minds.
Okay, well, I've got one more very specific question. Is the redevelopment of the lower Dawnlands? We've seen a lot of maps as to renaturalizing the area and redefining the mouth of the river and all of that stuff. Do you think the current plan that's kind of in the books is ever going to come to fruition, or is it got a lot of work yet to go?
Whether or not the plan itself is going to come into to be implemented, or whether or not it's going to be climate change ready.
Well, do you think we're going to see it in the next 15 years or not? Or is it going to stay much the same way it is?
I mean, there's a lot of variables that need to come together, but that's what people are hoping, is that there will be the investment and that it will be implemented sooner rather than later. What is the uncertainty associated with that calculation? I'm not sure. A lot of things have to come together to make that happen.
So you have no additional insight than we do.
Nobody tells us more than sort of the next, and it depends on investment on a number of levels in government as well as private capital and so on. But interesting that you bring it up in that. From a flood perspective, at least, I can speak to. It has been planned. The West Dawnlands and the revitalization of the mouth of the Don are being planned with Hurricane Hazel as the flood event that is being used to delineate where hazard exists and where it doesn't. So a pretty high standard there as well, and where possible, even additional capacity or protection above that standard has been applied. Like the landform on the west side of the Don, protecting those West Dawnlands in downtown, was actually built higher than it needed to be for Hurricane Hazel protection.
You're talking about sort of a freeboard, or
it was a freeboard based on sort of what could be practically achieved without completely disrupting the project budget.
Yeah, the case of the Hurricane Hazel flood hazard area in Southern Ontario is sort of a case where over-engineering or over-design kind of was okay. In this case, we had a lot of other benefits. We got the ravine system and park systems along the riverway. You don't necessarily want to have a football stadium-sized stormwater management plan in every neighborhood, but in some cases, over-design might not be so bad. And
as you say, Dan, that was a case where it was sort of a flexible and adaptive solution that had multiple benefits.
Yeah.
If the ravine or the flood hazard zone was defined in Toronto and surrounding areas on the basis of a 100-year floodplain, we wouldn't have the same open space and green space system. It wouldn't be nearly as big necessarily. So, that is a decision that was made that had all kinds of other sort of ancillary and public benefits. And there are other opportunities for doing that moving forward, without a doubt.
Green infrastructure,
even more intense protection and restoration of natural systems that have the ability to provide flood reduction and safe flood conveyance.
Well, if there are no other questions, we'll leave it at that. So thanks again, Ryan, for a great presentation.